Okay, so here we are, and this is the slide we were on last time, right? And once again, we can talk about AD philosophy is centralized, ECMA philosophy is distributed. So AD has PCP, which is responsible for the whole network, where here no node, single node is responsible. Everybody does the whole calculation. One beacon per sector, omnidirectional beacon per device. So here it is the number of beacons will be equal to the number of devices. Here it will be lot many more, because, well, it's not lot many more. It is one beacon per sector of the PCP. If the PCP has 8 sectors, it will have 8 beacons. On the other hand, if it has 100 devices, it's still 8 beacons. Okay? On the right side, it is one beacon per device, so there will be 100 beacons there, and maybe some dual beacons. PCP antenna training, all the devices, antenna training with all the devices. So here the PCP, since there is a central point, it has to be able to talk to all of them. It has this training with everybody, compulsory training, where you don't have to train, you just train with people you want to talk to. So less training. But again, they kind of spend a lot of bandwidth on the discovery channel. Here there is no dedicated control channel. Point to multi-point is easy because the PCP can talk to everybody. Here the point to multi-point is difficult because you will have to really train with everybody else. And ideal for data and ideal for video. That's the thing, because video is point to point generally, at least in a home. And data is, I don't know, could be multi-point. But the thing is, there are lots of data protocols that use multicast. So data things, even though you do point-to-point transfer, the routings and other things, they will not work if there is no multicast. Okay? Any question about 387 or 80? All right, we move on to the next one then. The next 60 gigahertz standard, actually, which came much before AD, was 15.3C. Now we will be covering whole 802.15 later on when we go into WPANs, personal area networks. But I think 60 gigahertz thing fits right here better, so I just put it here. And really there is no significant difference between PANs and LANs and things like that, because if they are defining a 10 meter LAN and 3 meter LAN, I don't know what is left for PANs. So basically 15.3C is a personal area network standard, and it does almost everything that the AD does. 2 gigabits over a few meters. It has 3 PHYs, single carrier. Basically, if you remember, we have 7 gigahertz of bandwidth. If it's 7 gigahertz, getting 7 gigabits or 2 gigabits is not a big deal. You just need you can do single carrier. And of course, you can do with OFDM. And then there are some special features for audio video that we will talk about, also with OFDM. So common mode signaling is basically, if you have devices which are all these different kinds, they have to be able to talk to each other, right? So that common thing is single carrier. So everybody has to, even if you're doing OFDM, you have to be able to do single carrier pi by 2 BPSK in the sync frames, so that you know what is going on. All right, now what is pi by 2 BPSK? It's next slide. But basically the idea is there is something common that all of the three speak. Beam forming in all three. So basically, just like we heard before, you have 2-stage antenna alignment, first sector level alignment and then beam level alignment. Then there is this new thing which comes up, and this is we haven't done before, is unequal error protection. UEP. Now you will hear a lot about UEP in the rest of this lecture. So previously in data, every bit was equally important. I mean, if you are sending a check for $3,000, which bit is less important? If you forgot a 0 or a 3 or anything, you'll be very unhappy. So the idea is with video, that is not the case. With video, if you have color bit or a density bit or brightness bit, if you made a mistake in the most significant bit, it is really bad. If you make an error in the least significant bit, nobody will care. Right? So here the bits are given unequal protection. And that is the special thing they do for video. Most significants are protected more than the least significant bit. And I have a notation which actually I consistently used because I wrote a book on this whole thing, not on this 60 gigahertz, but on FDDI, fiber data, where we had lots of issue of the big bits and bytes. B is always a lowercase for bits and capital B for bytes. Okay? And this is not a universal notation, and that's why you will find that many books will write capital M, capital S, capital B, most significant byte. And that gets confusing. Okay? But I have consistently used this little b in all the pictures and everywhere else and in every place I have written. MSB, and that's why it is all lowercase, it is a bit. And LSB is a bit. Similar things happen for the bytes too, by the way, because a lot of discussion about the bits and bytes when you send it things on the wire, because on the wire they are serial, in the computer they are not. And so you have to decide what to send first. Mac also have MSB, LSB subframes. So Mac also has. So media access control, what it does is it takes separate subframes. So it will take the bits, and treat them separately, put them into separate subframes because they have different protection. Now, what is pi by 2 shifted BPSK? So basically, a BPSK is very simple, binary phase shift keying. You send something at a 0 phase and the other thing at 180 degrees, which is pi by 2. No, sorry, pi, which is pi. So total is 2 pi. You send at 0 and pi. Right? So if your 0 is, let's say, 1, pi 1 minus 1 would be, minus 1 would be 1, right? Or you could do other way around, doesn't really matter, 0 and 1. Alright? Now if you shifted this by 90 degrees, then you get this. And this we call j and minus j. Everybody knows what is j. J is I, or j is the square root of minus 1, right, in the complex notation. So this is 90 degree phase, right, 90 and 270. So it occurred to somebody that, if you just have the logic for BPSK, you could alternate between these two things. So first symbol, for first bit you use this table, for the second bit you use this table, third bit you use this, fourth bit this. So you just do odd and even, odd and even. So here is the bit pattern, 1 0 1 1 1 0 0 1, right? For the first one we use this one, and I have used plus 1 as 1, and this is 0. So this is 1, this is 0. Alright? So 1 becomes, we use the scheme A, and it becomes plus 1. For 0, we use the scheme B. And therefore, 0 is minus j. For third bit, we use scheme A, it is plus 1. For fourth we use j, and so on and so forth. Okay? So now you get, this is what is which goes on the air. 1 minus j plus 1 plus j, 1 minus j, and so on and so forth. Now this has an error detection property. The error detection property is that if you didn't get a j after 1 or j minus, then you know that some bit is wrong. You have to alternate between 1 and j's. Signal signs could be different, plus and minus. But if you don't look at the sign, you have to go sin theta and cos theta, sin theta and cos theta kind of thing, right? So you get 1j, 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 j, and so on and so forth. So this has error detection property, right? And so this actually works, error detection probability increases by a factor of 2. Now, having said this, while the transmitter is doing BPSK, the receiver is really doing QPSK. The receiver is actually has to know 4 phases. Right? So yeah, you are getting the same effect as you would have gotten in QPSK. You could have sent 2 bits and then you could have had half rate. But here the sender is actually doing less work than a QPSK, I suppose. And so this is what is pi by 2 shifted BPSK, which is part of the standard in ECMA. Sorry, not ECMA. This is, I'm still in ECMA. This is in 3C. All right, so 3 phi's, single carrier phi will do BPSK to 16 QAM. So it doesn't go any more than 16 QAM. With 16 QAM, how many bits you get per hertz? 4. Right? So if you have 2 gigahertz channel, you can get 8 gigabits right there, right? Actually, the channels are more like 1.7 or something. So you get 5 gigabits very easily with 16 QAM and BPSK. And unequal protection is common. Beam forming is common. The channel size is actually common, except when you're doing audio visual, they probably needed some different number. And I don't understand why this is different number, but basically this is 1.6 for the high rate and 92 for the low rate. Okay, so basically they have 2 rates in the audio visual phi, and then they use different bandwidths. The key thing to notice is that with so much bandwidth, BPSK also does the job, and so they don't have to bother with OFDM. The MAC is very similar to other IEEE. It's a centralized MAC with a PicoNet coordinator, PNC. So now let me just say why it is similar, because these are the same guys who were working in this group. They went to the IEEE 11 group. This was done before. This was finished in 2009, was it, or something like that, and that was started in 2009. So they didn't have much to do differently. Anyway, so the thing is, they have PNC. PNC transmits beacons with a schedule. They have a super frame, as shown here. They have a beacon period, and then they have a contention and channel allocation period, right? And so basically, beacon period is when the PNC sends out the beacons, right? Contention access period is when basically you have to somehow let your demands be known, and then this is where you are allocated the time. Now, the contention access period cap has 2 parts: association sub-contention access period and regular sub-contention access period and the regular contention access period. So association basically means that you are going to do the training. Association means you are going to find your right configuration. Okay, and so that is basically the association part, and then the regular contention access period, this particular one, the last one, is more of a, what you call, letting the other guys know, letting the other guy know about what we are going to do. Okay, so okay, well, we are still in the MAC, yeah. So in the MAC, we allow aggregation. So there is a MSDU, multiple MSDUs aggregated. Now MSDU, if you remember, is like IP frame. MAC level service data unit, which is an IP frame. So you can take multiple IP frames, tiny frames, and put into one MAC frame. And the thing about that is, though, even though it is called one MAC frame, the acknowledgement is for the MSDU. So if suppose you send 5 MSDU in one MAC frame, because each of them has a CRC, we can check which one is not right, and it can ask you for the retransmission of that one. There is a group acknowledgement, so you can just acknowledge 5 of them at the same time. And then phi header indicates the type of MSDU aggregation. So there are 3 types of MSDU aggregation, and actually I have 3 slides coming up. First is standard aggregation, where you have large data frames. Low latency aggregation, where you have very small latency sensitive data. So this is not latency sensitive. So this is like you're sending a large file, and this is more like you are doing some kind of timely work. It could be even VoIP, but VoIP could go to the video part. But anything that is latency sensitive, but generally considered small frames, would go here. And then the AV aggregation, which is video. So we'll see what is the difference between these 3. Standard aggregation is used for large data frames, and therefore the fragmentation is allowed, because you might have, let's say, you want to send 6 1500 byte Ethernet frames. That is 9,000 bytes. And I think here maximum you may be allowed, let's say, 7,000 bytes. So you might have some frame that might be fragmented. All right, but you can put many subframes which may not be fragmented, and each subframe basically has an FCS. So just we talked about is that basically it will be acknowledged. Now for each subframe there is a subframe header SH, and for each subframe in the header there is basically the length. So how long is this thing? So you can figure out if there are a maximum 8 subframes are allowed. So let's say you have 5, then you will put the 0 for the 7, 6, 7, and 8 as the length. So that number is fixed. You have to have 8 subframes, 8 subheaders, 8-bit ACK, and so on. Okay. Each MSDU contains each subframe contains an MSDU or a fragment, and each has a CRC. And if you don't want to send it, you set the length to 0, and the ACKs are piggybacked. So this should be very clear, right? Any question about this? And by the way, there are 2 SCS here. One is the HCS, which covers the MAC header here, and the other one is the SCS, which covers this what we call MAC subheader. So that basically covers the length and the ACKs and the buffer size. And you know what is buffer size? It says Rx buffer size. So when you're sending this frame, you're telling the other side, look, I have only 7 megabyte left to buffer. So don't send me any more than that. So that is like a flow control. And this is the acknowledgement, and then this is the length of this. The second one is low latency aggregation. Now it turned out that this was not good enough, because 8 is not good enough for if the frames are just 64 bytes long. So 8 of them will make a very small frame, particularly at a gigabit speeds. You don't want to send in small frames because it takes so much time to train and so on and so forth. And therefore, they allow to 256 small frames, and that's why they had to put a different aggregation for them. 256. And now they could not just give you 256 bits like before, 8 bits. So they give you a variable number, and with each subframe you have to put the length, CRC, and so on and so forth. So you could put as many as you want, and the rest of the information, the aggregation information, will be found here in the subheader. And then some of these little frames could be using UEP, means they could be video or voice, which has different protection for different bits. right? So that modulation encoding scheme, MCS, is specified here. By the way, the real MCS is in the phi header, which says that this all the frames are encoded with this modulation encoding, but this one says that if it is UEP, then this is encoded with that modulation encoding. Okay, so UEP and EEP are both at the same time. EEP is here, UEP is here. What is EEP? EEP is equal error protection. Let's see. UEP MCS RX buffer, MSD requested rec number 1 is the last ACK received and res number 1 is the first ACK in this frame. So this is like TCP, where it says that, okay, I got your 95 and now I'm sending you the acknowledgement for 2003. Okay, so this one says I'm expecting whatever I'm expecting after, I'm expecting the acknowledgement for this number and I'm sending acknowledgement for this number. All right, here is the bitmap. Now and then there is a SCS covered. Okay, in EEP mode, MCS is indicated in the phi. In UP mode, UEP MCS is indicated in the MAC subheader. So I'm sorry, I'm not sure whether you can do both EEP and UEP in the same frame. I think what is happening is some frames will go with UEP, and if they are with UEP, then all of these subframes will be UEP and they will follow this MCS. If this field is 0, then they will follow EEP, all of them. Now this is one of the requirements for all the aggregations, is that everything that is aggregated has to go to the same destination with the same kind of protection. They cannot be going to different places, of course, because the MAC header will tell who has to receive it, and the same station will receive it and process it. So that's the thing, is that in UEP mode, MCS and the UEP MCS is indicated in the MAC header, and EEP mode, MCS is indicated in the phi header. Now AV aggregation is different, slightly different. Now audio visual. First of all, the video frames are large. So instead of 8, we can only allow 7. And now this is little bit arbitrary, it looks arbitrary to me, but they probably ran out of bits. You can only ACK 5 bits. Alright? So you take 7 MSDUs and you make them into 5 ACK groups. Come on. What a waste of time. But anyway, 5 ACK groups. So ACK group 1 consists of 2 MSDU, ACK group 2 might consist of 1 MSDU, and so on and so forth. You have to make 5 out of 7. And then the rest of the stuff is here, is MAC header, phi header, and so on and so forth. This is the MCS, which is indicated in the phi header. This is the length of the whole packet, and so on and so forth. Now, so there is this type for 1 through 7. And the type actually indicates whether it is command, data, audio, or video. All right. So this MSDU could be a command, says rewind. It could be data, just line number 6, or or some message to go flash on the screen, or it could be audio or video. Yeah.
Could you explain why the other two aggregations use block acknowledge bitmaps, but this one doesn't?
Yeah. Okay. So the thing is, let's see where the acknowledgement bit is. Type ACK group. So this is where the acknowledgement go, and so this is where the 5 bits are. What do you mean if there is no block acknowledgement?
Well, this one uses an ACK group, and the other two have a specific block acknowledgement.
Yeah. Okay. So basically, here it was that you had 8 bits. In the second one, you had maybe I don't know whether they have 256 bits or you just have some way of indicating which of the 256 were received. So there is a whole bit map, and here is a bit map of 5, length 5, a group. So video, the reason I am describing all this is to tell you how the video is slightly different, handled differently than the data, okay? And so I don't think this is critical that they make 5 out of 7. I think that is just a matter of having a multiple of 8 bits and then they ran out of some bits somewhere. And so the key is that they indicate, now this is the interesting part to me, is that they indicate here video header. So there is a video header here. There is a security header, the video header. Video header indicates the position of the first pixel of the video for the 4 video MSDUs. Out of 7, only 4 can be video. 3 have to be one of those other things. Alright? And the video has a position. So video has a position on the screen. So when a video frame comes, you have to say, well, it starts from this pixel and then it goes line by line by line by line by line by line, right? So every video MSDU has a position, and because video is transmitted at high rate phi, in the low rate phi you don't do any of this stuff. So this is so basically what is happening is, and this is the note I made, is that the MAC is application specific. So this is what we basically was not previously done, which was really you were what they call net neutral. You were totally neutral to the traffic. Right? Now here the video is treated differently than the rest of it, and therefore they even have video position. This should really be in the application header somewhere. Right? Instead of it being in the application header, it is in the MAC header. So it's quite possible that they are thinking in this case of bypassing the whole TCP IP stack and running the application directly on the MAC. Okay, that is the problem with that would be that you won't be able to go more than 1 hop. Right? Because if you want to do routing, you need something more. And so for 1 hop video, that's why they are saying, okay, well, and even for 1 hop, they could have put this in the video header. I mean, I really don't see why this has to be in the Mac, but I don't know. I wasn't involved. So this is application. So they have video header here, and then they have a security header, which is again something that the applications can do. And security header is normal, basically your passwords or certificate and things like that. AG group is here, and the type of what it is here. So 7 out of 7, 4 have to be video, and total 5 AG groups, and so on and so forth. Okay, let's see. I think we finished all of it. So extended control header indicates whether the frame is a beacon, ACK, or AV aggregated frame. Whether video header, security header, and extension header are valid. So it is quite possible that none of these are video. In that case, you don't really have a real video header, and so these are nulls. And so there is a bit here in the extended control header, which will say that okay, these bits are not meaningful. All right. So extended control header indicates whether the frame is a beacon, ACK, or AV frame, and whether the video header contains security header and the extension header. Right. Extension header indicates whether it is command data and all that. Phi header indicates the MCS, and 5 control field indicates UEP. So there is a 5 control bit right here. This is 1 bit, and it says that this is UEP. And then I think the MCS will be somewhere in the extended control header. It's not shown here, but this is just 1 bit. So it will indicate that we are using UEP. All right, and UEP is kind of common for video anyway. So security header indicates security is applied, and AG group field indicates if a MSDU is in the same AG group. Oh, actually this is not even an acknowledgement bit. It is just indicating how to deaggregate these things. So the AG group is 7-bit long. So basically 8-bit long, but the last bit is not used. So what is AG group? This thing here is that you have 7 MSDUs and you put them into AG group. So these two are in the same AG group. So this one will say 1, means I am in the same AG group as my predecessor. So this is 0. This is in a new AG group. This is in the same one. This is a new one, so this will be 0. This is 1, means I am the same as the previous one. This is 1 because I am in the same as the previous one. This is a new one, so this is 0. This is a new one, so this is 0. So for each of these you need a bit. So there are 7 MSDs, you need 7 bits. The last bit is not used, 8 bit total. So I am missing something here, which is why the AG group. But they have 7 MSDUs and 5 AG groups. And also I am missing one more thing, which is where the acknowledgement bits are. They might be in the control header, because we don't have the details of the control header here. All right, with those two things missing, we move on. So the summary of these 3 methods is that you can use different MCS for each frame, only in audio video. Not in low latency, but yes in this one. Okay, all right. Different MCS for each subframe. Now let's just verify that. Okay, well, that is only possible if you use both UEP and EEP at the same time, because there is only place for only two MCS, UEP MCS and EEP MCS. All right. So it is possible in standard, in video, audio it is possible, but these one are all going to one MCS. Then 8, 256 and 7, as we saw. Bidirectional, low latency data, in this case no, in this case yes. Now, so that's another thing, is a little detail that I skipped actually, I should have said this, is that when you get time for this one, these are little frames. So what you do is, you not only send them, you get the acknowledgement, and you can send them and you get the acknowledgement. So you can use the time for 2 directions at the same time. These are little tiny things. Even the 256 are allowed, generally you may not even have 256 frames. Okay? So this one is basically for request response time of protocols, where you have to send something at the response, request something, response, and all that. So that is why it is in one transmission allotment you do bidirectional. Best for video, yes, this last one. Fragmentation of video is not allowed here. Here fragmentation is allowed. Video header protected, in this one better protected, because FCS. Video header is protected here with FCS, SCS.
What does FCS stand for?
Oh, okay. So they use 3 or 4 different words. CRC is most common, cyclic redundancy check. FCS is frame check sequence. HCS is header check sequence. HEC is header error check. And HCS could also stand for header checksum. Although I don't think they use checksum these days, but IP does. IP is old. But nowadays we just use CRCs. All of these are CRCs. What is CRC? CRC cyclic redundancy check, that you do in a polynomial division. So FCS is frame check sequence. SCS is header check sequence. And yeah.
So you were mentioning that the subframes were small any notion, like in bits or bytes, how much that is? Or
How much is small?
yeah.
Oh, small could be 1 byte. I mean, see, the thing is, unlike Ethernet, if you want to send 1 byte on Ethernet, you have to make it I think 48 byte or so with 16 byte of error. 64 byte is the minimum Ethernet size, right? Here there is no minimum size. Because in the Ethernet, the minimum size comes from the CD part, collision detection part. Here there is no collision detection. And maximum, obviously, you know, because maximum is that this whole thing has to be less than 7,000 bytes or something like that. So you can't have any more than that. Okay. All right. So they have three different schemes. That finishes actually our 802.15.3c. And the key things to remember are that they have three different files: single carrier, OFDM for data, OFDM for video. And more often than not, this is a result of people coming from different companies. People coming from video companies, they want to see things one way. People coming from data companies, they want to see things other way. And so you end up with two different alternatives for the same thing. Okay. Now you know pi by 2 BPSK. Right? So basically, that gives you better error protection without significant transmitter cost. Receiver cost is same. Unequal error protection. Third thing you learned in this particular part is that protection does not have to be equal. That is the key. Then there is a coordinator, central point of control, which sends the beacons and schedules the transmission. And then there are 3 aggregation modes: 8 for data, 256 for little data with latency sensitive traffic, and latency sensitive traffic can be bidirectional. And then there is AV, where you have 7 with 5 A groups and 4 video streams. Okay. The last thing is wireless HD. So wireless HD is HD from the TV guys, you can see. So this came from the television industry, not the IEEE. And they wanted to use 60 gigahertz to connect television, displays, laptop, Blu-ray player and all that. And it is designed for high quality uncompressed video, because video doesn't need gigabits, by the way. People have been saying that, why do you need gigabits? I want to watch video. But video, we are watching, all of us are watching video right now, and that is in megabits, right? Because it compresses so much. So the only justification for gigabits is uncompressed video. So here is the thing that you could do with this: 2560 by 1440p pixels, 60 hertz, 36-bit color. If you do all of this, which we don't do that much, I mean, actually you might do actually on the, you might have a screen on your desk which might have this much pixels and 60 gigahertz and 36-bit color. You will get 8 gigabits, and that's why you need the cable, right? But this is a cable replacement. By the way, now you can buy much better. I mean, if you go to Walmart now, you will find this one 60 got to 120, and then 240 hertz TVs are available. And this one goes to 4K by 4K, 4000 by 4000. All right. And I think colors probably stay there, but the thing is, if you really want to do uncompressed on that one, you will need a lot more. So this is lossless 3D 480-bit. Okay, there is a 480-bit color, 246 hertz refresh, 4K resolution for smartphones and tablets. So that's their justification. And what we are making here is what they call a wireless video area network. So you heard of PAN, LAN, now there is a WAN. Video area network. 10 meter is the distance. 4 channels at 1.76 gigahertz, very high data rate. Now, so you could do channel bonding in this case. So you could get 7-8 gigabits per channel, and you could bond 4 channels to 28 gigabits using spatial multiplexing and 4 concurrent streams. So you could just do 4. A non-line of sight operation. Alright? And wireless HD has a good document, overview document that you can download, and it's easy to understand because this is not the spec, it is an overview. The problem with the spec is it doesn't explain why. So if you read 356 pages of ECMA, which I did, I mean not really read word by word, but basically it doesn't tell you why dual beacon. It says you will send dual beacon, period. So there is no explanation, none required, because it just people already know. But so this is better. This is overview. You can read it. And wireless HD is real. Wireless HD is real because if you go to Amazon, you will find these things available for purchase. Okay? And so it's here. It has 3 files: high rate up to 7 gigabits, medium rate up to 2 gigabits, and the low rate up to 40 megabits. This is for mobiles. This is for TVs and DVRs. The low rate is for basically omnidirectional control and discovery. So when you want to find people, you just come down to the lowest rate, and then that way you can send your signal in all directions. For multicast, for X, for HRP, MRP, antenna beam forming, and capability exchange. So all of these are mostly what we call multicast stuff. Now HRP and MRP are very similar except for these rates, and therefore most of the time they talk about HMRP, which means HRP or MRP, either one. HRP is high, medium, high or medium. So basically there are 2 kinds of things, HMRP and LRP. Okay? And since they use the same band, same frequency band, let's say you use channel number 1, all of them will use channel number 1. And somebody is using HMRP, somebody is using LRP, they will do their time division multiplexing, which is actually common. So this is all very similar to what we have seen so far in the other 3. Peer-to-peer. So again, this is ECMA philosophy, no access point, but no, hold on. Actually, this is not totally distributed like that. It needs a coordinator. So this is more like the IEEE side. A device may have a coordinator capability, and generally display and storage devices will have this capability. So if you have a big TV, you paid $1,000 for the TV, you might as well have coordinator in that one. But if you have a little tiny $100 phone, maybe you will not have it. But I cannot see how you will not have it, because if you don't have it, you can't talk unless there is a coordinator. So general displays and large storage devices, if you have a DVR or something, they will be a coordinator. So again, you can see one more thing, that this was done just before 15.3c. So a lot of this went into 15.3c, and a lot of 15.3c went into 1180, right? And so things are very similar. I could have done them in the time order, but I thought it's better to do latest first. So maybe you're seeing this backwards. So wireless HD has coordinator and everybody else. Everybody can transmit and receive the low rate, but some can receive high and some can receive medium. So some may be able to do only this. And shut down in sleep modes. So basically people can shut down, except if you're a coordinator, then you probably don't sleep very long. You can sleep too, but basically then everybody else is sleeping in the night. And then there is a channel estimation, just like before. You do the training and you find out how the channel is. and then there are higher layers. So the thing is, above the MAC, they also define some more layers which are above the MAC, which we will not go into. But those are for video format selection. You could say, well, I like this kind of coding, video coding, encoding, and so on and so forth. But that is higher layers. Now, I put little bit more detail here so that I wanted to introduce you to what we go through when you are when you are working in the wireless. And so, I would have skipped this kind of detail before, but I just wanted to explain to you because this is sort of something important. Is that so? This is what we call wireless HD HRP parameters. Now there is similarly MRP parameters, there is similarly LRP parameters, and generally when you have parameter for this is for OFDM. So I wanted to show you how the OFDM systems are designed because I have gone through the similar tables for WiMAX and for other places. Okay, and so first thing you decide is how much bandwidth you have. So they decided 1.76 gigahertz. And what is your sampling rate? And with some calculation, which is actually is not just one way down, it is some kind of trial and error kind of thing. So they decided that the sampling rate should be 2.5 gigasamples per second. So that is FS. How many subcarriers? 512. So that means that their period for FFT would be the ratio of these two. NSC, which is 512, divided by the gigasamples. So that is FFT, which is the fast Fourier transform, will have to deal with samples every 200 nanoseconds. All right. Some of that time goes into the gap, and some of that time goes into the data. I mean, real thing. Okay. So now, what is the subcarrier spacing? So you have 176 gigahertz, and you have this TFFT. So 1 upon TFFT is 4.975 megahertz. So if you remember that the subcarrier diagram where you have 512 of those subcarriers, the distance between the subcarriers is 4.9 megahertz. And this should be delta, it should have been symbol rather than the symbol, delta FSC. So this is the subcarrier difference. So now the guard interval is 64 divided by Fs. 64 guard interval is I forgot why this formula. So anyway, formula is 64 divided by this 4.9. So 64 divided by 4 is 25 nanoseconds. And so this is the guard interval. You subtract from that, you add that TFFT plus TGI. This is the total symbol duration. Okay. So actually, I just want to explain. I probably said something wrong here. Is that this is the total symbol duration is 226. Out of that, 25 is the gap, and then 201 is where the bits are. So number of data carriers. Out of 512, 336 are data carriers, 3 are DC carriers, and 16 are pilots. So I have already explained you what is a pilot. What is a pilot? Yeah, to estimate the channel. To send in the pilot, you just send whatever a well-known sequence, and at the other end you figure out how good that channel is. But I haven't explained DC carriers. I want to explain you DC carriers, and then these are the null carriers, and these are generally at the end. They could be in the middle too, but generally they're at the end. These are the guard carriers. So these protect you from the neighbors anyway. So DC carriers. Generally you have one DC carrier, and DC carrier is right in the middle. And that is your, what they call, basically when you have this much band, right in the middle is your DC carrier, so that way you figure out where your middle is, and that is generally sent as a null. Basically, there is no signal is sent on that one, and so there is a gap there, and with the gap you can figure it out that this is where the middle is, and this is where my first, second, third, fourth, fifth, sixth subcarriers are. Right? So that is null, but they have 3 DC carriers. So they take not only the middle but also the next 2, and those are sent as zeros. I mean, there are basically no signal on those 3. There is no signal on 157. 16 are used for estimation, so that leaves 336 number of the data carriers, right? And then you use QPSK or whatever your modulation is. Then the outer code is read Solomon 224.216. So what happens is when you get the bits, you take 216 bits and use a read Solomon code to make 224 bits. They have 2 codes. First they take these long bits patterns and then add some error correction bits on that. So that is 216 to 224. Right? That is read Solomon code. So basically the number of extra bits are only 8 bits. Right? Then you do inner code, is that you take 3 bits, you take 1 bit and make 3 bits. 1 and 2. 2 bits to make 3 bits. Take 5 bit to 6 bit. Right? So there is another level of error correction. So now there are 2 of them for HRP. EEP, you know what EEP is and what UEP is. Unequal error protection, you use 2, 5, 1, 2, 4, 5, whatever, and then EEP these. Now, why they were selected, and obviously the reason is you want to keep the number of bits, extra bits as small as possible, and at the same time, correct as many errors as you can. But I wasn't really able to figure out as to why they have 1/3 here, and they have, some other numbers here. So that is something. Maybe the way UEP is done is that you take the lower half and the other upper half, and then you combine them. So the net is this. Comes out 2 5s as opposed to 1/3, 1/2. But anyway, so these are 2 different inner codes specified. Now the similar tables exist for every wireless protocol that you have seen, whether it is 11A, whether it is 11N, whether it is 11G, AC, AD, everything that we have discussed has a similar table. I have just skipped it so far. I was going to cover it in WiMAX, but I thought this might be a good point. So let's just go and see that you understand all of these except for this 64 upon FSC. Generally, the way we used to do in WiMAX was that we took the total symbol duration and divided by 1/8 or something. Here it looks like it is 1/8, could be 1/8, I don't know. So 1/8 of that is the guard interval, and the rest is the data. 7/8 is the data.
It should be the FS. It's 64 over 2.5538.
Okay. Okay. But why 64? Okay, it is 64 is 1/8 of 512. The thing is, the way we did it in WiMAX, as I'm telling you, is basically not this formula, but we just took the symbol duration divided by 8. Okay? And so that formula would have been better if I would have written here this line first, and then 1/8 TS is that, and then and so on and so forth. But this is approximately that number, same number. And as I said, there's a typo here, as Ian pointed out, that this should be 64 divided by FS. FS is 2.5. So 64 divided by 2.538 is this nanoseconds. All right. So the key is, let me just one more time emphasize. The key is that given a bandwidth, given a number of subcarriers, so if I gave you 1.76 and I gave you 512, you should be able to figure out that, okay, if I divide this by 512, I get some number, some megahertz. Okay, that is the carrier spacing, because you're going to put, right? And then some of those carriers, basically 512, we have to put into into guards, into pilots, into data, and now you know the DCs. Okay? And then, given the number of carriers, you can figure out what is the data symbol size actually from this one, and some of it has to be put into the gap, which is the guard interval, and the rest goes into the data. Okay? Any question about this? Yeah. Symbol. Yeah, so this is for each symbol. So every time you will have a 201 nanosecond of data and followed by 25 nanosecond of interval. That will make up a total of 220 nanosecond, and then again you will have data, gap, data, gap, data, gap, data, gap. Okay, the next detail we have to do when we are designing wireless networks is the spectral mask. So basically, again, this is a detail that you can live without, but I think somewhere you will run into it. And if you read my papers, you'll find that this is all there in the papers. So, I had to run into it. Basically, the idea is that you have to tell the world how they should use the spectrum. The standards have to tell the world. So, it is defined by this kind of diagram which says that at the central frequency, you will have this power, whatever power you have. And we call it 0 dB relative. So, this is the power, maximum power that you generally have at the central frequency. 0 dBr, decibel relative. Then when you go to 1.1 gigahertz away from the center, you should come down to minus 20 dBr. If it is any more than minus 20 dBr, you would be illegal. Alright? When you go 1.6 gigahertz, it should be minus 25 dBr. When it is 2.2 gigahertz, it should be minus 30 dBr. And generally these things are symmetrical, so you on the other side as well. So basically the idea is that here basically this is overflow into the next channel. If your channel is 1.76 or something, your channel really ends here. And this is overflow into the next channel. Right? That overflow should not be more than minus 25 dBr. Alright, first of, right? So that is the kind of idea, and much of this actually here is so low power that this is guard interval. That's why they keep the guard carriers, and that they don't really use. So they are mostly going to use this part here. Okay, so there is a spectral mask, and the spectral mask basically tells you the relative power as a function of frequency. And the relative power is specified in dBr, starting from 0 dBr all the way down to a low value. Now this kind of mask, any of these standards that we have talked about so far, everyone has it. And everything that we will talk about later has it. And this kind of table, every OFDM system has it. Okay? And so I just put it here. I could have put it at a later place, but now that we did it here, now we'll see in WiMAX and LTE. Alright, that finishes that detail of the wireless. Now MAC. So the MAC consists of random access and the channel time. Random access, as the name indicates, for unallocated communication, and channel time is for pre-allocated communication. All right, this is same like we had in 11, point coordination function, and DCF was distributed coordination. So the coordinator announces the number, length, and positions of CTBs and RTBs, and before starting a new WAN, stations scan for the set of channels. It will select the least busy HMRP channel and select an LRP channel within that, and becomes the coordinator. So basically, if there is no if you want to start a new W WAN, you look channel 1, channel 2, channel 3, channel 4. There are 4 channels, I think. 4 times 2 is 8, yeah. So 4 channels. You look at that and see which one is least busy, and I'm going to use that channel number 3, let's say. In that channel, you will start HMRP and some area for LRP, low rate, and HM is high and medium rate. If more suitable coordinator comes on, the coordinator may hand over responsibility. So there is this possibility of handing over right in the same area. So if the TV turns on, the HDR may say, okay, all right, you take over the responsibility. And to new coordinator, so for example, DTB is higher priority than STB. What is STB? STB is set-top box, right? Centralized access, more like is 15.3C. Coordinator controls all the access. All stations make a request to the coordinator. Coordinator allocates the time. Station transmit on the specified time. So basically, this is nothing new. You could have isochronous traffic or asynchronous traffic. Isochronous means you will have time in every frame. So you, for example, when you are watching a video, you might want a half an hour request. You don't want to go in every frame cycle and ask for the time. You just get it once, and that is isochronous. Asynchronous is you get it when you need it, and it is the total time needed once and allocated multiple frames. So you could say, well, I have a 30 gigabyte file to transmit, so I need so many seconds. You might not get all of those in once. You might get 5 microseconds now, 5 microseconds in the next frame, 5 microseconds in the next frame, 5 microseconds in the next frame. So that is distributed over until you are done. Asynchronous. Now the next detail is, and this is important, is that allocations are announced in nth beacon but used in the n plus first superframe. And this is another thing that I noticed in many standards, and so this is common, is that here the beacon will say, okay, so I am giving you 5 microseconds, but you cannot just use it in this frame. You have to use it in the next frame. Similarly, when this says here, I am giving you 5 microseconds, that you use it in the frame after. So that way you get time to get ready for that. Otherwise, suddenly somebody tells you, you have to transmit 10 milliseconds, and suddenly they say, where is my queues are not in order right now. So they give you time. So you get the whole frame time to get ready for the transmission. The whole allocation is done one frame before. Okay? So that's what this is showing. The beacon, this is the beacon. This tells you n plus first frame allocation. And this is the beacon for n plus first frame, and this is the showing allocation for n plus second frame. If too many stations, child VWAN or drone VWAN are started. So actually, I wrote the word child VWAN. Their word is drone VWAN. I don't know why they call it drone, but this is basically you could start a small group on another channel. So the stations first join the main channel, and then they start with the into the drone VWAN, drone WWAN, VWAN, WWAN. All right, power save mode. This is very similar standard stuff. Active stations back up simply to listen to the beacon and deactivate electronics for the rest of the super frames. A station can tell the coordinator and go to sleep. They do not wake up for every beacon. When a station wants to transmit to the sleeping station, it tells the coordinator announces in the subsequent beacons. When the station wakes up, it tells the coordinator, and so on and so forth. So the idea is, the main new idea here is that the coordinator does not buffer. Coordinator just buffers the request. So the coordinator keeps announcing in every beacon, number 1, number 3 wants to talk to you, number 1, number 3 wants to talk to you, number 1, number 3 wants to talk to you. When number 1 wakes up, 1 and 3 get together. All right. As opposed to in 11, the data was buffered at the access point. Here there is no access point, and therefore it doesn't have, the coordinator may not have extra buffer and all that for this purpose, so they don't take that responsibility. So it just remembers who wants to talk to whom, that it does remember. The next thing is the device control. So you can say one touch play, you can say power control, timer programming, deck control, tuner control, all kinds of things that you do in video is possible through this protocol. So summary of this is things to remember, that this wireless HD is clearly designed by the television people, by the television industry, for uncompressed video cable replacement application. They have 3 PHYs, high rate, medium rate, and the low rate. LRP is used for discovery and multicast. There are no access point, but some devices need the coordinator capabilities. You need at least one coordinator. The time could be random access or CTBs, which is the channel time, pre-allocated or allocated on demand. And then there is a power save mode. That is simple to remember. That brings us to the summary. Key points: 60 gigahertz, also known as millimeter wave, has large bandwidth. Lot of bandwidth there. That is a good point. Has a small antenna, which is a good point. You could have lots of antennas. So I could do easy beam forming and gigabit speeds, but it has a short distance. That's the negative point. Now the tri-band devices are coming, which will have 2.4, 5.8 and 60 gigahertz. 11AD uses a central control point, and they introduce the word PBSS. And I forgot. What is PBSS?
Personal BSS.
BSS we know, basic service set. And anyway, ECMA 387 is fully distributed.
Yeah, personal.
And then 3C is similar to AD, and wireless HD is very similar as well. In all cases, antenna alignment and tracking is required. So that's the thing, is it might take few microseconds. Now, I have added one more slide, and that is actually not very critical, but it is interesting, is that what is Google Trends? How many people know what is Google Trend? All right, those of you who don't know, just Google Trends. And then you can look how many people are searching for the word. And it's very interesting. So I did this. So here is the graph. ECMA, nobody is looking for it. Ever. You see, this is the time from 2005 to 2013 to today. Okay? 15.3C, yeah, little bit, but nobody is looking for it right now. Wireless HD, a lot. Okay, so you can see what is alive, what is dead. Right? However, that the AD has come in, HD is going down, AD is coming in. It's very easy, very cheap, very free method to find out what is happening. Alright? Then I did another thing, Google search. I said ECMA 387 plus site:.com. What does that do? To find out which companies are providing information about 387. Right? 2,400 results, mostly from book publishers. So you find IEEE, Explore, IEEE not .com, but Wiley.com, things like that. So that shows you that there is no product which is implementing ECMA. Wireless HD had 1.1 million results, and mostly from eBay and Amazon. People are selling it. Okay? And 15.3C has 18,000 results, mostly from publishers and some chip makers. So yeah, chips are being built, but are built or something like that, but no products I could find, right? 11AD had 18,000 results, mostly from publisher and chip makers. So this is just coming in. And the chips are becoming available. Products are coming in. This one has a products already. You see? So this is the information. Rest is as standard. Reading wise, there are 2 Safari books and this wireless HD specification overview. These are really easy to read. I would really like you to read these 3 things. There is a bigger list at the end. on references. These are things that I read, but I wouldn't want you to basically, it's not required you to read it, but they are available. Okay? All right, we didn't get to your question, but hopefully we'll do that on Monday.